Morning everybody, and welcome back. Great to be here again. So yeah, my name's Nigel Wood from the Met Office. I work in the Dynamics Research team, which is a small group that looks after the fluid dynamics and numerical methods aspects of the unified model. So I'll just briefly run through what I'm going to try and cover in the next 40-45 minutes or so. I'll give you a brief introduction to the unified model. Hopefully a lot of you are already familiar with that, but I'll just go over that again. I'll define some notation and nomenclature, and then I'll spend a bit of time describing the semi-Lagrangian scheme, which is the scheme we currently use in the unified models to transport things around. I'll focus in on some aspects of our current dynamical core endgame and the transport within that, and then try and explain, well, does all this stuff I'm talking about make any difference at all? Talk about a couple of conservation-specific aspects of conservation, and then finish up by looking a little bit to the future, a project called Gung Ho that we're running to develop a next generation dynamical core. At the end of the slides, you'll see there's a bibliography, some references there, and also with thanks to Chris Smith, details on some of the transport options in rows that might help in the practicals later on. So the unified model, what is it? So it's unified in the sense that we use the same model to do all our operational type forecasting, right from NWP, the forecast that you see on the television, on the daily, when they're running at high resolution over the UK or whatever area of interest, right out to the very long timescale climate simulations at relatively coarse resolution. And then everything in between that, so the regional climate predictions, seasonal predictions at about 50, 60 kilometers. And then we do a lot of research work at very high resolution for process parameterization purposes. That might be down to as small as 10 meters, certainly a few hundred meters, and I'll show an example of that in a minute. And it's worth noting here, particularly for my later slides, that this whole structure, the model itself, is about 25 years old now, so getting on a bit. One of the challenges of that is if we have a unified model running from these very coarse, very long timescales to very high resolution, very short timescales, we need a numerical scheme, a single numerical scheme that can work at all those resolutions and timescales. And so here, this is a map of what the impact of a 4-degree warming on the Earth's climate would be. So that was run at a resolution of about 300 kilometers, but run for a very long time, 100 years or so. This is an example of a weather chart that we might use for forecasting the weather for the next few days, out to 5 days or so. And that typically that might have an effective resolution, say, of 30 kilometers or so. And then we're running in quasi-operational mode. We're running a very high resolution model at a third of a kilometer over London, so to better predict the fog, for example, at Heathrow. And so we have this huge range. There's a factor of 1,000 between the resolution here, 300 kilometers, and here, 300 meters. And yet the same numerics has to work well across that wide range. So it's quite a strong challenge for us to meet. And I'll explain the schemes that we use at the moment that allow us to do that. This slide, I sometimes worry that this is a bit of a promotional slide or a marketing slide. It isn't. This is really just trying to say that we've met that challenge, but we have to do it so that things are accurate as well. And so what this is doing is comparing the Met Office performance across a range of skill indices, so surface pressure, geopotential height, the winds at both near surface and higher up over a wide range of times, and we throw all of that together into a single index to tell us how well the model is performing over the northern hemisphere, and we then compare that with other models. And then we normalize it so that the Met Office always sits here at 0, and below the line is good. And unfortunately, we do have a model that is better than us. That's the European Centres model, their medium range forecast. And then we have a whole load of other models here, which are in a pack behind us. So this is sort of saying that the model, we have challenges to make it unified so that we can run it across a range of things. Doing that in itself, one might say, is relatively easy. Doing that and making sure that the model performs well is a much harder challenge. And I'll probably come back to say a little bit more about this at the end. Okay, so that's something about what the unified model is and what we're dealing with. And now I'm going to go into talking a bit more about how we actually move things around from a fluid dynamical point of view in that model. And I'm just going to introduce some notation. So I'm going to talk about the density here, rho, denote that by rho of a quantity of a species X, and that is the density, sometimes in the chemistry field more known as the concentration or the mass per unit volume of some species X. In particular, D denotes the dry air, so that's the density of the dry air, and then I'm going to talk about mixing ratios, which is the ratio of the density of a species X to the density of the dry air. And by definition, the mixing ratio, therefore, of dry air is 1. Then we have 4 different ways of looking at the equations that govern how we transport things. We have a conservative form and we have a non-conservative form, and I'm going to start by looking at the conservative form. And then within each of those, we can have 2 ways of looking at it. We have an Eulerian viewpoint and a Lagrangian viewpoint. So the Eulerian viewpoint is where we sit still in a room like this and we watch as flow moves past us and we measure how things change relative to where we are. We then have a Lagrangian view, which is where we sit on that parcel, if you like, in a hot air balloon, and we move with that parcel. So here we're looking at the first of those is a conservative form, and this one is the Eulerian form. So the natural quantity to look at there is the density, as I defined on the last slide, or the concentration, and the rate of change of that is determined by the divergence of the flux of that quantity into or out of some fixed Eulerian volume. We can translate that into a Lagrangian form, where here this big d by dt means the rate of change of something as we sit on that parcel of air, and we now have to integrate that density over that volume. And so this then says that the rate of change of the mass within that Lagrangian parcel does not change. So that's one way of looking at that, and we'll come back to that a little later. But the alternative form is what's known as the advective form. So this is not a conservative, not naturally conserving form. And this is the natural form for mixing ratios, for example, the ratio of the density or concentration of a species to the dry air within that volume. So mx is the mixing ratio here. And again, we have 2 forms. We have the Eulerian form, where now that divergence form becomes simply an advection form, u dot grad. Or in the Lagrangian form, we have this very simple, very nice equation that simply says the Lagrangian rate of change of the mixing ratio is 0. So that's just some background to the equations. And then I'm going to talk about the semi-Lagrangian scheme for moving stuff about, which is the scheme that we use within the unified model. And for mixing ratios, which is what we use within the model, then this Lagrangian form is the natural form. And as I said, that simply says that the rate of change of some quantity, f, is 0. The rate of change of that following a parcel of fluid is 0. And so how do we translate that from this simple equation into some numerics that does the work for us? So we can think about what this means, and we can integrate this equation. And the natural way to integrate this, since that is a capital D by dt, a Lagrangian derivative, the natural way to integrate that is along a path following the fluid. And if we do that, then what this equation says is that if we have some parcel of air here that is labelled in some way by its mixing ratio or its number concentration F, then if that's labelled in some way, then as we follow that parcel, the air parcel itself may change, but the label associated with that will not. And the path along which we go is denoted here by this dx. And because this is following the parcel, following the air, then we know that dx by dt is the velocity of that air parcel. So we can write down what that means, having integrated this equation along the parcel of air. It says that this function, the mixing ratio, whatever you want, at the new time level, t plus delta t, at the new position, x plus dx, this increment in its position vector, is the same as f at the previous time level at the old position, provided we satisfy this equation so that dx by dt is determined by the velocity of the fluid. So that's how a Lagrangian scheme works. We then have two implementations of that one can think about. There's a fully Lagrangian approach, or there's what's called the semi-Lagrangian approach. In a fully Lagrangian approach, that is all we do. We simply track that parcel of air. We start with a whole load of parcels and we move those forward in time and we simply keep track of where they go. So we know where they end up at the end of, I don't know, 24 hours or 24 years. We simply follow those. And that's the basis of the name model. Particle dispersion model, we simply release the particles and we follow where they go. There are some disadvantages to that, and what can happen is that we can end up with a very inhomogeneous distribution. So we can get clustering of particles perhaps near boundaries or in areas of convergence. We end up with very few parcels of air elsewhere where we might still want to know what's going on. And so we end up having to do some interpolation or aggregation to where we need the answer. So in the unified model, what we do is what's known as a semi-Lagrangian scheme, and this tries to take the best bits of both worlds. So it tries to take aspects of the Eulerian scheme that we like, but combine those with the aspects of a Lagrangian scheme that we like. And I'll explain how we do that now. So the basic principle of a semi-Lagrangian scheme is that we are always considering what happens, how things change at fixed points, so at arrival points, at grid points, where we want to know what the answer is. So this might be our mesh. Currently operation, we're running at a 10 kilometre weather forecasting mesh, so we might think of one of these points as that arrival point. So this is a mesh point where we want to know what the value of a quantity is. And how we work that out is, for the transport, what we do is we do a backward trajectory. So we ask, well, where did this air come from at the previous time step? So we solve that equation, dx by dt equals u, the velocity of the flow, and we backpedal, if you like, from this arrival point and ask, well, where did that air come from one time step previously? So for the global model, that's 4 minutes previously. We say, where did that air come from? And it will land someplace here. And in general, that isn't going to be a grid point. It's going to be somewhere within a grid box, within a grid cell, away from the grid point. And so what we have to do then is, having worked out where the air comes from, we have to estimate what the value of the air here is by using the values surrounding that grid point. So we interpolate from the surrounding grid points to that point. So there are two steps. First one is to evaluate the trajectory, i.e. where is this departure point relative to our grid point of interest, the arrival point, and then we have to evaluate whatever the field is we're interested in at that departure point. So what are the pros and cons of this approach, this semi-Lagrangian approach? One of the key points from a weather forecasting point of view is that it has excellent dispersion. And what do I mean by that? What I mean is it captures very well, very accurately, how waves propagate through the atmosphere. And of course, getting the wave propagation right for gravity waves, Rossby waves, is key to getting the weather forecast right, getting the timing of events as fronts come through. We want good dispersion properties. And it turns out that the semi-Lagrangian scheme has that. We also want an appropriate level of scale selective damping, and the amount of damping in the scheme is determined by how we do that interpolation. And I'll come to it later. We use cubic Lagrange interpolation, and that is a damping scheme, but it's very scale selective, so it damps the high frequency, the short wavelength modes, preferentially to the long wavelength. So as long as we're resolving something well, then we get a good level of damping. Key, though, perhaps the most important property is that it has excellent stability properties. And so in terms of what time step we can use, how long the time step we can use for a given resolution is, then that is determined by a physical time scale. So effectively the shear, if you like, in some sort of three-dimensional sense, so d vector u by d vector x. I won't go into details of what I mean by that, but it's a physical timescale of the shear in the flow, rather than what an Eulerian flux form scheme typically is bounded by the numerical timescale, the velocity divided by the grid spacing. And so that means that if we have flows where there isn't very much shear, but there's a very strong wind, then we can use a relatively long time step because the flow isn't changing. So it makes, that's the Lagrangian aspect coming through to the scheme. So that's, as I've just said, that's particularly beneficial in large-scale flows. For example, where we have very strong jets, we can use a relatively long time step. But perhaps crucially for us at the moment, and I'll come back to this later, in polar regions, in the global model, in polar regions, we have a very small grid spacing near the poles. And for our current operational model, that is as small as 12 meters. We run, as I've said, with a time step of 4 minutes. And you could ask then, well, what wind speed do we need for the Courant number, the number that typically determines the stability of an explicit or an Eulerian scheme? What number of wind speed would violate that condition? And it turns out to be something as small as 5 meters per second. So I can probably walk about as fast as that if I'm lucky. And so it's very small. And so very quickly, if we used an explicit scheme, then we would have to use a very small time step, or we'd have to substep the scheme, and that has efficiency issues. So I'll come back to this in terms of where we're going in the future. This is just an example, work done by Kohei Aranami from JMA when he was visiting us, and he set up some idealized flow that you'll see in the next slide. And this is the Courant number, and we can see it getting up to numbers of, what's that, nearly 4 or 5 in the regions of the poles, in the zonal direction, and in the meridional direction, we've got values of, well, certainly greater than 1. And what he did was initialize some tracer with this so-called slotted cylinder shape with very sharp gradients, and then let that go in that wind field that I showed earlier. And we get very strong distortion, but we can see it behaving very nicely in the region of the poles, where, as I say, the Courant number there is much larger than 1. So we've got this very nice, very good stability within the model, but also reasonable accuracy. So that's all the benefits, and there's inevitably some disbenefits, and I would argue there are 2 main disbenefits to the semi-Lagrangian scheme. One seems a bit paradoxical, and it is exactly what allows us to get good stability, and that is that it's a non-local scheme. So if we run it with a large time step, then where we're looking for that departure point can be a long way away from the arrival point. So that's great for stability, but if you're running on a very large modern supercomputer with a lot of processors, what that can mean is that your departure point can be a long way away from the processor you're working on. So you have to go off to this other processor and gather information from that, and that can cause what they call communication bottlenecks, which will slow down the code. So from that point of view, there's an efficiency disbenefit. Perhaps the bigger one from a general point of view is conservation, and the scheme does not in general conserve what it transports. So there's lack of conservation. I'll try to my best on the next slide, on this slide and the next one, to explain why that is. So here I'm thinking of using a semi-Lagrangian scheme to transport this quantity m about, and we here have a 1D array of values of m at a number of points. This is the previous time step grid, and then we have the values at the next time step. And what we do to evaluate this value at the next time step, we have an arrival point, we calculate its back trajectory, and we find that it lies somewhere, say, in between these 2 values. We then form a stencil. We take the surrounding points, so in this case it would be these 4 points, and we do an interpolation, a cubic interpolation of these 4 points to give us a value of xd here. If we now look at the next grid point, the next value of m at point I plus 1, we do the same thing. We have an arrival point. We go back here. we look at the stencil, we do an interpolation, and we get this value here, etc., etc. Now, if the scheme is conservative, then all of this mass, if you want to call this a mass, all of this mass here should end up being divided somehow amongst these points here. And so what that says is that the amount of mass at this point that goes into creating this departure point value, plus this amount that goes into creating this departure point, plus this, plus that, should all add up in some normalized sense to 1. So we should redistribute all of this mass between these 4 points and distribute them amongst these new values. Unfortunately, that does not happen with the semi-Lagrangian scheme, with the interpolation scheme that we use. We use a pointwise cubic Lagrange interpolation, and that has the property that all these values add up to 1, so that it preserves a constant, but there is no constraint on these values adding up to 1. And so we can lose or gain mass. I won't run through that. This slide simply says in maths what I've tried to explain on the previous slide. And so I will just skip that. I should say on the last slide, it's true if the wind is uniform and we have a uniform grid, so there are special cases where we do get conservation, but in general we won't get conservation. And I'll come back therefore to what we do about that in the next few slides. So endgame, the even newer dynamics for global or generic atmospheric modelling of the environment, is the term we use for our current dynamical core, so the dynamical core of the unified model. This became operational in 2014, and there's reference there. So in terms of the transport, endgame uses a semi-Lagrangian scheme for all the variables within the model. There's some special aspects for vector aspects, so even for the wind field we use a semi-Lagrangian scheme, and that gives us headaches because we're then moving something whose bases change as we move from the arrival to the departure point. I won't go into that, but there's some special aspects there for those who are interested. So we use a Lagrangian interpolation for everything, but we use different types of Lagrangian interpolation. So in the horizontal, we use bicubic for all variables, so that's what I've been talking about before. So in 1D, that means a stencil of 4 grid points in each dimensional direction. In the vertical, though, for reasons that I'll come back to in a minute, we use cubic interpolation for the wind components, so effectively we're doing tricubic for the wind components. We're using a thing called cubic Hermite for potential temperature and the moisture variables, and I'll explain what that is soon. And then in the vertical, we use quintic interpolation for all other tracers. So that then has a stencil of 6 points rather than 4 points to give us improved accuracy in the vertical, where typically there's a strong stratification of variables. So on the other slide, previous slides, I've explained why the semi-Lagrangian scheme on its own does not conserve aspects, but for us that's important, particularly for you guys on the chemistry side, making sure that you preserve at least the first moment of chemicals is key for long-term simulation. So what do we do about that? So we now have various options within the model, but I'm just going to focus on what I would call the standard options. So we have this thing called a Priestley algorithm after the guy at Reading University who invented it, and I'll explain briefly how that works. That's applied to moisture and tracer value variables, and now also potential temperature. That's changed within the last year or so. So effectively that can be applied to all our variables. Monotonicity, something I'll explain in a minute, but basically we don't want the scheme to produce spurious new extrema, either maxima or minima, that aren't there in the data that's being moved around. And so we need to manage that, and we use a scheme called Bermejo-Staniforth scheme. Again, that's optionally, the user can determine whether it is or not applied to the moisture, tracer and potential temperature variables. We also use the semi-Lagrangian scheme for the transport aspects, for certain aspects of the dry density quantity, and of course dry mass, conserving that is key, otherwise our model will simply run out of stuff to do anything with. And so it's a relatively small change, but without the mass fixer, then we get a relative change for about 10 to the minus 5 per time step. So relatively quick, it's a small amount per time step, but it doesn't take that many time steps for that to become a significant impact. But it's a very uniform change. So what we do is we apply a multiplicative fixer every time step to patch that up. But what we found in the global model certainly is that it's important that that fixer preserves the potential energy. Otherwise, we get some very strange results going on in the dynamics. And so we simply apply a fixer that is a function of height, and we calculate this A and B to preserve the dry mass and also make sure that we don't change the potential energy. So I'm just going to explain now a little bit about how that conservation algorithm, the Priestley algorithm, how that works. And the key idea behind this is to note, well, where are we losing why haven't we got conservation? It's coming from that interpolation scheme, as I tried to explain, the 4-point stencil. It also argues that if we go with if we change the order of the scheme, so if we have a low order, not very accurate scheme, or we have a high order, very accurate scheme, those two will have different amounts of mass loss. And so what we can do is compare the difference. We can compare how much mass we lose using a low order scheme with how much mass we lose with a high order scheme. And then we know where those two things are different is telling us where there's a sensitivity to that interpolation. So if our low order scheme and our high order scheme effectively give the same answer, the same amount of mass, then we needn't worry. We believe that amount of mass is correct. Where they're different though, we think, well, the interpolation is doing something here. It's getting something wrong. And so it's those areas where we know to make a change to the mass. So it's trying to do things locally, but ultimately it is a global correction. So that's what I've tried to say here, where the two schemes, a low order scheme might be linear compared with our high order, cubic or quintic. Where they're different is where conservation is being lost. And therefore, in those regions, it's where they're different, is where we change the high order scheme proportionate to that difference. And then we add all of that up over the globe, and we fix those constant of proportionality to make sure that we conserve the mass. So it's a non-local scheme that tries to make it as local as possible. So that's the Priestley scheme for conservation. And then the other thing I mentioned about is this Bermejo-Staniforth scheme for monotonicity. Now, if we take this high order schemes, for example, cubic or quintic, and we apply it to smooth data, so very smoothly varying, then that isn't going to introduce any new maxima or minima. But if we think about applying it, say, to a step function, then what we will find is we will get spurious increases and spurious decreases in the tracer that we're advecting around. And we don't want to do that. For example, for moisture, that could lead at sharp gradients in moisture to the model predicting negative values of moisture, for example, or new peaks in a concentration field that mean that something else happens in a nonlinear sense. And so what happens there is that high order, going to this higher order is not appropriate where the data is not smooth. We need the data to be smooth enough to support the order of accuracy we're trying to impose. And so a sensible way of doing this, and there are options to do this in the model, is to simply reduce the order of the advection, of the interpolation progressively. So we might go from cubic to quadratic, check whether that's monotonic or not, and if it still isn't, go to linear. That would be one way and quite an effective way of doing it, but it's relatively expensive. And so what we do with the Bermejo-Staniforth scheme is take a pragmatic approach, and that says that we simply limit the interpolated value to lie within the bounds of the data that's being used to interpolate it to. So we go to this departure point, we look at the values surrounding that departure point at the grid point values, and we don't allow the interpolated value to go above or below the maxima and minima implied by that data point. So a very simple scheme, but quite effective. Okay, so I'm just going to say, does it matter? I've prattled on about what we do and why we do it. Does it make any difference? So this is some work that was done by David Walters and people in his team at the Met Office. And here, I don't know how well this comes out, but here we're looking at the zonally average temperature from a 20-year AMIP run. And we're plotting, this is 90 degrees north, 90 degrees south, and this is from the surface up to 10 hectopascals. And this is the zonally average, zonally mean temperature field from endgame. What we've then done is look at, well, how does that compare with era interim, a reanalysis, our best guess at truth? How does that compare? And in endgame, if we look at the difference between endgame and era, that reanalysis truth, then what we see is a very large warm bias in the region of the tropical tropopause. And this new dynamics was the old dynamical core that endgame replaced. And if we compare that with era interim, then we see a relatively small bias, still there, but much smaller than endgame. And if we look at the difference between the two, then we see about a 2 Kelvin increase in that bias. So this is not good news. So something we've changed had an impact on that. And this will try and explain why that is. What we did in moving to endgame was basically move away from a centered scheme, a second order centered scheme, to what should be a higher order, third order scheme using this cubic Lagrange interpolation. The problem is, if we think about what's going on at the tropical tropopause, we have a potential temperature profile that might be characterized by this sort of dog leg, where we have a uniform gradient up to the tropical tropopause and then a change in that gradient above it. And if we think about what's going on with the cubic Lagrange scheme, when the vertical velocity, well, I should just start by saying, if we have an inversion such as we have at the tropical tropopause and we move that up and down, then after an even number of oscillations, we should get back to where we started. The potential temperature shouldn't change. What we're seeing here is that it does. We're getting this warming going on. And what's happening is when the vertical velocity is positive, then the departure point for this point near the tropical tropopause is here, and the stencil that we use to compute that is these 3 points. And in particular, that means that these 3 points are determining the gradient of potential temperature as we move it up and down. So this, if we think about what advection is doing, that is like minus w d theta dz. And with the cubic Lagrange, we are then using these 3 points to determine that d theta dz. However, when the vertical velocity then changes direction and we move that inversion down, then the stencil changes. The departure point becomes here, and we now have a stencil that looks like this, and the gradient is being predominantly determined by these 3 points. And so as we move up, we have one gradient. As we move down, we have a different one. And so that lack of symmetry leads to this warming of the tropical tropopause temperature, which is not good. What we had before was a centered second order scheme, which always, whether W is up or down, has the same stencil size, and we approximate that temperature gradient by a single value, whether the wind is positive or negative. And so we don't get that bias, or at least not so much. How can we mimic that in a cubic, in a semi-Lagrange sense? And the way of doing that is to use a cubic Hermite scheme, where we use values. We estimate, instead of using a 4-point stencil, we use a 3-point stencil, but we make estimates of what the gradient is at this point. And so if we now go through the steps, if we start with our new dynamics, the old dynamical core, then here we have that bias of 2 degrees that I mentioned, and we might characterize that advection scheme for temperature as a second order centered scheme. We then move to cubic Lagrange, which is what I showed you on the slide 2 before that, and that leads to this large bias. If we then change to this cubic Hermite scheme, then we pull back quite a large amount of that bias, and we've almost got it down by 2 degrees. If we then move to conserving the potential temperature using the Priestley scheme that I mentioned before, then we get what is actually a very good, it's still a warm bias, but a much reduced warm bias compared with what we had before, and actually an improvement on the previous model. So that argument is just trying to say that what we do does matter, does make a difference, even in something as complex as the full unified model. I'm not going to spend much time on this, but this is just to let you know that there are alternative ways of achieving conservation, and you may hear about slice. If one wants to use a semi-Lagrangian scheme and get conservation, then we have to work in a conservative form. So that means going back to using densities rather than mixing ratios. And if we want to use a semi-Lagrangian scheme, we have to translate this equation into what I've already shown you, which is a more of a Lagrangian scheme for the mass of an air parcel. And what we could then do is, just as I did before, where we had d by dt of mx, we integrate that along the trajectory. We can now do that for this equation, but now we have to evaluate this volume integral along the trajectory. And that is something that some schemes, including SLICE, which is a scheme that we played with, developed for some time, does. But so instead of transporting a single point back and evaluating the point values, we track back where a box, a volume, the arrival volume comes from, and we have this irregular volume, and then we have to do a remapping. So instead of interpolating to a point, we're remapping across a volume. But that comes with cost, and so that is something, and there are accuracy issues, so that's something that's available within the model, but is not used or actually recommended, actually. The other aspect I'll talk briefly about, because certain areas are moving towards running limited area models for long times, where conservation can become an aspect, become an issue, is conservation in limited area models. And I won't say very much about this. This is looking at, again, it's some work that originally Kohei Aranami did, and then more recently Mohamed Zerukat has followed up on, is looking at how one can impose conservation within a limited area model. In the global model, you have a closed domain, so it's very easy to know how much mass you have at the beginning of the time step and how much to impose at the end of the time step. In a limited area model with a semi-Lagrangian scheme, that is not so obvious. And this plot is showing, well, how does the mass change? So we have this is a big brother experiment where we know how much the mass should be changing within this limited area. And this measure is how much does it change with time. If we just do a semi-Lagrangian scheme applied to whatever this tracer is, then in fact it doesn't do a bad job. This is the red line along here. It stays quite close to what it should do, 0. But if we then add on monotonicity, which we want to do to make sure that we don't get any overshoots, undershoots, new extrema, then that actually messes things up quite badly. And so what we see from this is that the conservation scheme is principally correcting errors introduced by the monotonicity scheme. And then there's some I think it's the blue line here, is this so-called PLF scheme, which is a way that Kohei and Terry Davis developed of imposing mass conservation within a limited area model, and that returns us to a value which is close enough to 0. So that's just to say we can do it. Those options are available within the model if anybody wants to do them. Okay, so in the last few minutes, what I'll talk about is where we're going in the future, and hopefully try and say we're not being too gung-ho about it. To start with, I'll just motivate, well, why are we interested in changing things? One of them is the conservation. So we would like to improve conservation and have an inherently conserving scheme. The other, the principal driver, though, from a dynamical point of view, from running the weather forecast, is the supercomputers of the future. They're just throwing more and more processors at us, and we need to make sure that our codes can scale well and make good use of those supercomputers. So how well are we doing at the moment? So this is what's called a scalability curve, where we run the model on a certain number of processors. So here, 7,344 cores. We then run it on an increasing number of core count, and we look at how quickly, what the time to completion of the model is on those cores. So if we double the number of cores, if we had a perfectly scalable model, the time to completion should halve. And that's what I plotted here as a red line. Well, I didn't plot it, Paul Selwood and Andy Malcolm did, with thanks to them. If we had a perfectly scaling model, then the time to completion normalized in this sense would lie on this line. Here, they've run Endgame, our dynamical model, at 6.5 kilometre global resolution, so not about 2/3 of the resolution we are currently running. And there's a positive and a negative to this. What we see is that even at these incredibly high resolutions running on, at this end, 88,000 processors, Endgame is still scaling. We are still getting benefit from running on an increased number of processors. So that's a positive for me. The negative, though, is we're quite a long way away from perfect scaling. And so in a sense, you could say, well, we're not, if we double the number of processors, that takes probably at least twice as much power. We're not getting twice as much benefit from it. We're only getting something 60% or so. And so what can we do about that? Well, the first question one has to ask is, well, why is that? Why are we not scaling perfectly? And this comes back to principally what I was talking about earlier, and that's the resolution near the poles. So we run on this lat-long grid. As I said, operationally, we have a 10-kilometre resolution over the region of the UK. But if you just look at the geometry of what's happening as we move closer and closer to the pole, those meridians where we store the grid points are getting ever closer to each other, and the grid points themselves are getting closer to the pole. So there's a quadratic effect going on here, non-linear effect. So a 17-kilometre resolution, the grid spacing here was about 35 metres east-west. Now at 10 kilometres, the spacing is 12 metres. If we wanted to get down to 1 kilometre and do some heroic grand challenge run, then that actually reduces to 12 centimetres, which is absolutely bonkers. Even at the 10-kilometre spacing, I haven't given a talk like this where I couldn't fit 2 of those grid points in the room I'm speaking in, which is madness. And as I've said, communication between the processors is what is slowing us down. And so this is something that we can't keep up with. So Gung Ho was a project that put together between the Met Office, NERC academics, and the computational scientists within STFC, the Science and Technology Facilities Council. And what it boiled down, Gung Ho means working together harmoniously, which of course the 3 of us were, and very rapidly the academics came up with a backronym, Gung Ho, globally uniform, next generation, highly optimized, some say highly optimistic. But basically what the project boiled down to was trying to work out what sport to play. Moving away from the lat-long grid, should we replace it with a triangular grid or a hexagonal grid? Maybe we should go with the volleyball approach, and that's a cubed sphere, 6 sides, or with quadrilaterals, or go with the yin-yang, the tennis approach. And so we spent 5 years looking at all the pros and cons of these different meshes, looking at the numerics on them and how we might maintain accuracy. And the one we're pursuing at the moment is this cube sphere mesh. And so I'll just finish up by saying, well, where are we? As I said, the cube sphere is the principal contender. The challenge for us from a dynamics point of view is the lat-long grid has some very nice properties. It's an orthogonal grid, whereas moving to a cube sphere grid that we want to, that doesn't suffer from singularities at the corners, is a non-orthogonal grid. So getting our numerics to work well on that has been a big challenge. And to rise to that, what we're using is this so-called mixed finite element spatial discretization. So we're moving away from the finite difference, finite volume approach of the to a mixed finite element scheme. I said that conservation is important. At the beginning of the project, we sent out questionnaires to various users. We didn't get very many back, but all of the ones that came back weren't worried about dispersion properties or finite element. Conservation was the #1 priority for them. And so what we're doing is moving away from a semi-Lagrangian scheme to an Eulerian flux form transport scheme, and in particular a finite volume one as we're exploring. And this is just an example from Stephen Pring in my group of taking a strip of something, a strip of the tracer that stretches from the North Pole to the South Pole, and just moving that around with a solid body rotation in a conservative way. So we're redesigning the unified model. As I said, it's 25 years old. The code, the software within that is 25 years old. We're moving to something a bit more modern, something that's only 15 years old, Fortran 2003, but still presents the compilers with challenges. We're moving to this separation of concerns where we're moving the computational aspects out of the code. So we're separating the natural science from the computational science to try and make the whole thing future-proof. And we're targeting the mid-2020s, which when we think these supercomputers are hitting the exascale. And I won't dwell on this, but I'll just flick through these three slides as a bit of eye candy for comparisons between Gung Ho here and Endgame. This is a very high resolution, so 50-meter resolution, where we drop some cold air up here and we let it fall down here and then run along the surface, and we're getting good comparison between Gung Ho and Endgame. This is, we call it the mountain test, but that's bit of a misnomer. This is a very small perturbation to the surface that then triggers mountain waves, non-hydrostatic mountain waves, and again, good comparisons. This is larger scale. This is about a kilometre or a few kilometre resolution between Gung Ho and Endgame. And then this is a larger scale, the baroclinic wave test case. So this is now on the full 3D sphere, and we're just letting a baroclinic wave develop and comparing that between Gung Ho and Endgame, and again getting very good comparison now at 1 degree resolution. Okay, and I'll stop there and take any questions. Thank you for listening.